State two feature of stationary wave that distinguish it from progressive wave. Now you can take two of explanation that amplitude of vibration stationary wave is vary from zero amplitude to the maximum amplitude and antinode. Yeah, but in progressive wave all points have the same amplitude. Okay, so the wavelength is twice the distance between adjacent node or antinode. Yeah, two adjacent nodes and antinode. So this is two adjacent nodes and twice of two adjacent nodes. In progressive wave, we have the same phase. So, example, I begin. So this is I draw a progressive wave. So if I start the point here, where the one full wavelength, if we is lay on the point with have same phase, yeah, same phase. So this is one wavelength. But in stationary wave, this is one wavelength has opposite phase, yeah, it's opposite phase. The particle over here and here is out of phase 180 degrees. The nodes and antinode do not move along the string. Yeah, the nodes it's remain at that place, but just change, but sometimes going up, sometimes the displacement going down. Where most with the crest and troughs move with the velocity of wave. Yeah, it's move because it's progressive wave that transfer energy, and then the particle will move when the previous particle after the previous particle move. Yeah, it's propagate. There is no translational movement of energy, but the energy is associated with the wave. Yeah, no translational, no move. The energy it's keep at that place. Yeah, no transfer energy, but in progressive wave that energy transfers. Between adjacent node, all point of stationary wave vibrate in phase. Yeah, between this is, yeah, it's going up together. Yeah, between two adjacent node, all the particle here it's going up together. It means the wave is vibrate in phase. The particles vibrate in phase. All the particles are there at the same instant. The particle between two adjacent nodes are 180 degrees with the next two adjacent nodes. So this is with the next two adjacent node is 180 degrees. All the points here, all the particle here, the phase is 180 degrees. And there are only certain frequencies of stationary wave possible on the string. Yeah, it's it creates a it's mathematical series of frequency. The allowed frequency depend on L. Yeah, that's what makes stationary wave different with progressive wave. Okay, you can take only 2 points. A long tube is open at one end, it's closed with the other end by means of piston that can be moved along the tube. A loudspeaker producing sound of frequency 550 Hz is held near the open end of the tube. Blah blah blah. Read the question. So L is 45 when the when the loud sound happen, the L is 45. The speed of sound tube is 330, so that the wavelength of the sound in the tube is 60. Okay, because we have frequency, we have the speed, so we can calculate wavelength to v divided by frequency. How much this it's equals to Yeah, it's equals to 0.6 meter or 60 centimeter. On a copy of figure, mark all the position along the tube. Okay, so the wavelength is 60. The wavelength is 60, but the L of the tube is 45. Yeah, 60 to 45. How many wavelength we have? So one wavelength is 60, but the length of this L only 45. So how many wavelength we can take to fit in 45? One wavelength is not enough because it's longer than the L. The wavelength is longer than L. Okay, we divide it by 2, we have 30. We have one wavelength and 15 to be 45. Okay, it's quarter wavelength. Okay, so we have half wavelength and quarter wavelength. It means we have 3/4 wavelength here. Okay, so just throw 3/4 wavelength in this 45 centimeter. Okay, piston always end by knot. This is always end by NT knot. Yeah, 3/4. This is half. This is a quarter. Maybe, yeah, maybe this is too long. Yeah, you can make it perfectly more perfect than me. Yeah, you can change the position of knot here, where the wavelength it's drawn equally. Okay, so we have two knots and we have two empty notes. Yeah. The frequency of sound produced by loudspeaker in B is gradually reduced. Determine the loss frequency at which loud sound will be produced in the tube of length L equals to 45 centimeters. Okay, so the lowest frequency in open tube is great with with quarter wavelength. So one wavelength in the question before, one wavelength is equal to 60 centimeter, and then quarter wavelength is equal to 15 centimeter. Yes, so the lowest frequency is phi per lambda. I'm sorry, it's not the way it is. Oh yeah, sorry. Um, we have to see, that the length of this piston, I'm sorry, we have to make it fit with the length of piston. So the length of piston is 45. Yeah, the length of piston is 45, and it occur and it create quarter wavelength inside this 45. Yeah, because the frequency change, and then the length of wavelength also change. It's not 60 centimeter anymore, but the length of the tube is constant. So wavelength is equals to 180 centimeter, or it's equals to 1.8 meter. And then the lowest frequency is phi per lambda where v is, and then the result is 1 83, or we can run down into 180 hertz, or we can use the series of frequency in open tube where the open, okay, the question is formed in the second frequency. Why? Because it create 3/4 wavelength. It's mean 3 frequency. Yeah, it happened in the second pattern of stationary wave in open tube. Remember that the series in open tube began with 1 frequency, 3 frequency, and then 5 frequency. Yeah, and so on. Yeah. So so this demonstration show in 3 frequency, and then to get lowest frequency, we just divided the second frequency, 550 hertz, divided by 3 to be the lowest frequency. Yeah, this is another way. So the first frequency is, yeah, we still get the same result. Okay, next, a string is stretched between two fixed support. 3.5 stationary wave are generated. Yeah, blah blah blah. Read the question. Distinguish between node and antinode in stationary wave. Okay, node, uh, when the particle is at rest. Yeah, no displacement in node, no displacement, and the antinode, the particle move maximum. Yeah, displace maximum. I'm sorry, displace maximum. So this is maximum amplitude. State the phase difference between vibration of particle at any two neighboring antinode. Okay, neighboring antinodes. So this is antinode and this is antinode. The phase is 180 degrees. Yeah, because they are happen out of phase. Calculate ratio frequency of mode vibration shown here to the frequency of, oh yeah, so we see here we have 5 loops. Yeah, we have 5 loops. So remember the pattern in string, pattern of stationary wave in string is n part 2. Okay, so first frequency it's half, second frequency is 2 per 2, third frequency is 3 per 2. Yeah, it's happen half wavelength and full wavelength and half wavelength. It means the stationary wave in string have a series 1 frequency, 2 frequency, 3 frequency, 4 frequency, and 5 frequency. We can see this is the 5th frequency of stationary wave in the string, and the ratio to the first frequency is 5 and 1. Yeah, this is for the 5th frequency and this is for the first frequency. Last question, the frequency of calculate the speed. Okay, so this loop happen in frequency 160 hertz and the length of the string is 3.5. Calculate the speed. Okay, so we must find how much the wavelength here. So we have two half wavelength, or it's equal to 5 per 2 wavelength. It's happening in 3.5 meter, and then one way of lying is 1.4, right? 1.4 meter. So V equals to lambda times frequency, where lambda here 1.4 times the frequency 160, and it's equals to 224 meter per second, or 220. We round down to 220 meter per second.